All right, so last time what we did was we did start this section, which is, again, Chapter 8, Section 1. And I'm pretty sure I did this last time, but let me say it again. Here, what we're going to deal with is a system of equations. So we're not going to just deal with one or two equations now. What we're going to deal with is a collection of them. So we're basically going to deal with a collection of equations at the same time. So we're going to see what a system is. And what I just said wasn't the precise definition. However, it is the basic idea. What we're going to focus on, though, is a system of linear equations. Linear equations, what I mean is, the variables have their exponent is only 1. It's kind of like what we saw, I think, in 1.1, if I remember correctly, or 1.1, that's right. You had something like 4x plus 1 equals 5, something like that. Right? The exponent of x was 1. It's not like a quadratic equation where you had x squared. Excuse me. It's not like that. We're also going to see different ways of solving it. We're going to see one method with substitution. We're going to see a method involving solving them graphically, which basically means, graphing them. And we're also going to see the method of elimination. Now, I'm also going to go through Desmos today. I know I probably should have gone through it before, and I am sorry about that. Although it's not too hard to figure out, but I am going to go through Desmos today. Graphically, it's going to be kind of quick, mostly because being an online class, I'm not going to have you guys graph it by hand. If it was if I was teaching this and we were all actually on campus in class, then I would have you guys graph it by hand as well. So the graphing part, that will be kind of quick. Excuse me. And then we'll see another process called elimination, which is really nice. I know some students prefer that method, the method of elimination, as opposed to substitution, which I can understand. So it's a nice method. They're all really nice methods. So, all right. But now again, just like, any other science, or maybe not just a science, I guess, but any subject, I guess, there's always going to be some kind of terminology, right? There's always going to be some kind of, definitions. And that's what we have here. So basically here, what a system of equations is, it's just a collection of equations in the same variables. That's just what it is by definition. It's just a collection of equations in the same variables. That's what it is by definition. All the equations could be in variables x and y. They could all be in a third variable, x, y, and z. Z we would treat as a variable, but we're going to focus mostly on x and y. I forgot what course number it is here at SUNY Oneonta. I do know there is a math course. I think it's linear algebra, I think it's called, but you basically go more into this stuff. There is actually a lot of matrices in this subject. The area, what we're doing right now, that is. But that's a different story. But basically here, what we're going to do is only focus on this kind of system here, where you have a times x plus b times y is c, dx plus jy is k. This is where a, b, c, d, j, k, these are all real numbers. They're constants. What has to happen, though, is a and b, they can't both be 0 at the same time. So in other words, at least one of them must be non-zero. Same thing with D and J. I mean, if A and B are both 0 at the same time, well, then you really only have one equation, right? That takes all the fun away. Same thing with D and J being 0 at the same time. You don't want that. You know, we don't want that. Okay. So now what we want to do with these system of equations is solve them. That is, we want to find what's called the solution. And a solution to a system of equations, you want, it's an ordered pair that is a solution to both equations. Let me say that again. A solution to this system of equations is basically okay, 3 times the charm. A solution of a system of equations in 2 variables, in the variables x and y. It's just an ordered pair that's a solution to each equation. So you have to be a solution to each equation in the system. That's really what I'm saying, what I'm trying to say, and I finally said it. So you have to be a solution to each of these equations. That's what has to happen. Okay, good. It's going to be an ordered pair because we have 2 variables here, x and y. And this is just an example. I might have even done this last time, but I feel better doing it again. Mostly because in the other class, if I remember correctly, I didn't get up to this point with them. So I want everyone on in the same page, so to say. Let's check if 3,1 is a solution to this equation. Well, let's see. Remember, we want x is the first number, y is the second. That's the idea. So if x is 3 and y is 1, are the equations true? That's really what we're asking. So if x is 3 and y is 1, 2 times 3 minus 1, well, that's equal to 5. Is it? Well, we get 6 minus 1, and we get 5. That's true. So that's good. What about the other equation? 3 plus 2 times 1. Well, is that equal to 5? Well, yeah, that's 3 plus 2, which we know is 5. So this is a solution to both equations. It satisfies both equations. That's great. Because of that, this is a solution to the system. This is a solution to the system. Now, what about this ordered pair, 4, 3? Is this a solution? Well, if you let x be 4 and y be 3, is that going to be true? In other words, is this a solution to both equations? Well, if x is 4 and y is 3, in the first equation, we get 2 times 4 minus 3 equals 5. But that is true. That is true. We have 8 minus 3 is 5. Yeah, that's true. So it's a solution to the first equation. What about the second? Well, is 4, if we plug this into the second equation, right? Do we get a true statement? If x is 4 and y is 3, we have 4 plus 2 times 3, which is 4 plus 6. Is that going to be 5? Well, no, because we get 10, and 10 is not equal to 5. So this is not a solution to the system. It's not a solution to the system. Okay, so it's not a solution. And this is some more terminology with these systems. Basically, what can happen is this, and what's actually really nice about this kind of system, there's either going to be only there's only 3 cases here. There's either no solutions, there's only one solution, or there's infinitely many solutions. So there's either no solutions, only one solution or infinitely many. And that's what's going to happen here. And it turns out if there are no solutions, we say the system is inconsistent. And remember, the solution set, that's just a collection of all the solutions. That's all. I mean, I'm not really going to focus too much on solution set. I'm only mentioning it because the book does. That's all I'm doing. So this is what it means to be inconsistent. But if a system has at least one solution, we say it's consistent. So here we found a solution, right? Since we found a solution, this system is consistent. Now, if there are infinitely many solutions, the equations in the system, we say they're dependent. That's if there are infinitely many solutions. And if there's only one, though, we say that the equations, they're independent. So if there's only one, that is, if the solution is unique, and we call it a unique solution, one unique, one of a kind, then we say the equations are independent. So are these dependent or independent? Well, we actually don't know. I mean, yeah, this is not a solution, and we found a solution, but that doesn't mean that we don't know if 3, 1 is the only solution. I mean, it could be, but we don't know. There could be infinitely many more solutions. I mean, 4, 3 is not a solution, so it wouldn't be part of that solution set, but there could still be infinitely many solutions.